hopefully you can see where your mistakes are happening. If you haven't thought about putting your tests together and sort of identifying your problem areas, you should do so soon. There are, like I said, 24 days left. That's quite a bit, but other teachers are going to start throwing stuff at you as well, right? So it's time to sort of start getting yourself a little bit organized. Connor, you take that, you're better at this. Okay, so let's have a look here. Page 1. An object in orbit around Earth only appears weightless when it is actually free falling along with everything around it.
True.
Absolutely 100% true. Everyone should have got that. I don't recall if everyone did or not. I marked it a while ago. Number 2, you may not have remembered, or you might have missed that day or what have you. That's your responsibility, though. If you were sitting half as far from your nearest classmate, in other words, if you moved closer to them, the gravitational force of attraction between the two of you would be 4 times as strong. And that is true. Inverse square law. If you move twice as far, 1/4 the strength. So that is true as well. For any pair of surfaces, the coefficient of static friction between the surfaces is less than the corresponding coefficient of sliding friction. That's false. Static friction is always greater than or equal to. Nick, if you want to go in the back, you can. It's up to you. Okay, now number 4 may have caused you to think real hard, and that's what it's supposed to do. And again, I'm not a big fan of multiple choice, but I'm trying to train you for the future, and you are going to see, if you're taking any science at university, you will see multiple choice. Your weight is properly defined as, it is A, the gravitational force which Earth exerts on you. That's the best answer out of that. Certainly not the amount of material, that's your mass. It is not the force you exert outside the bathroom scales, because you or the scales could be accelerating. And you know what I should have sent? I should have sent the scales with you guys to Toronto. How would you felt about carrying the scales down to the CN Tower and riding? Probably wouldn't have done it, would you? No. Walking down the Yonge Street with your bathroom scale? No? Yeah, silly. Number 5, your weight on board an orbiting space station would be B, only slightly less than normal, because your weight is defined as the gravitational force which Earth exerts on you. You would just feel weightless, and your scale would measure weightless, but your actual weight would be just slightly less than normal. Bit of a trick. Okay, now number 6 is a bit of a, you have to do a little bit of, it's a 2-step kind of thing. If you weighed 112 newtons on the moon where the gravity is 1.6, how much would you weigh on Earth? So you have to find your mass and then convert that back to newtons on Earth. It's a 2-step thing. Is it a little unfair?
Yes.
Well,
I get it.
I don't know. I mean, if you weigh that against the fact that you could just guess, right? You got a 20% chance, I guess. So you're going to take the 112 newtons, solve for mass with 1.6, so your mass is going to be 112 divided by 1.6. Someone help me out here, I have no calculator. I get 70 kilos. Then you're going to go, weight force is mass times gravity. Take your 70, multiply by 9.8, 686, and then you got to do that stupid scientific notation thing, right? So that's B. That's a lot of work for 1 mark, isn't it?
Yeah.
I should have made it out of 2.
Yeah,
Well, I got it right. Yeah, I got that too.
Yeah, and all the people that got it wrong will be complaining.
Well, it depends on the way, I guess.
Is it a bit of a stretch? Yeah. Can you do that? Yeah, you should be able to do that. You should know enough to do that. If the strength of the frictional force is equal to the applied force and oppositely directed, and assuming that all other forces may be ignored, the object may be at rest or moving at uniform velocity. In other words, the forces are balanced, right? If the friction force is equal to the applied force and oppositely directed, and assuming that all other forces may be ignored, in other words, the net force is 0, which means the acceleration is 0, which means it could be at rest or moving at uniform velocity. So the answer is E. Number 8, feeling of apparent weightlessness which astronauts experience in orbit as a result of their motion, which is best described as
Free fall.
free falling.
Wait, number 7 is A?
No. E. Acceleration is 0, therefore the answer is E. Number 8 is free falling. Number 9, it's evidence from experience that it's more difficult to get a heavy object sliding than it is to keep it sliding. This is because the coefficient of static friction is greater than the coefficient of kinetic. And I also took starting and sliding and various other possibilities. Number 10, for some reason, caused way more grief than it needs to. First of all, if you're going to be told to give examples of desirable and undesirable, you have to clearly label them or explain. You can't just give me 2 examples and make me guess which one is which. Okay? I didn't even have an answer down here because there's thousands of examples, right? When is it desirable? When you're trying to stop, right? On the car, when you're on the road, right? You want friction, right? Undesirable, maybe when you're, right? Mileage, yeah. Okay, trying to push something. I mean, there's countless examples, but you have to explain which one's which. Nick, you need one of these. Okay, let's get into the problems here. Number 11. Okay, this is a straightforward horizontal motion one. Some of you really need to do a better job of identifying from the question what these quantities are, because it's causing you grief. And I can't say this enough, you have to practice. It's like anything. It is like a sport, it is like music, it is an art. You must practice. And it may not be fun, but if you want to know how to do it, and you did register for the course, you've got to do it. A force of 10.6 is applied. That is the applied force. 10.6. To an object mass 1.4. I had several people give me 1.4 was equal to something besides m. It accelerates at 1.6. I have 2 or 3 people solve for the acceleration and got a different number. Determine the force of friction. You're solving for FF, and the coefficient. Those are the things you're solving for. Okay? From the mass and the acceleration, what can you get?
The friction.
The net force. F net is equal to ma. 1.4, the acceleration is 1.6, giving you a net force of 2.24 newtons. Well, hold on here. I thought we applied 10.6 newtons. How can I only get a net force of 2.24? Friction. Friction. Like, what do we have here? We've got an object with an applied force, and there is a friction force. It asks you to find it. That's the cue that there's a friction force. So, the net force is the applied force plus the friction force. What's the net force? It's right there. You solve for it. Notice how I lined up the equal signs here. 2.24. The applied force is 10.6 plus FF, giving me a friction force of 2.24 minus 10.6, negative 8.36.
You got one right.
Okay, now the next step is to find the mu. Mu is FF over Fn. We have the FF part. We don't have the normal force. It's equivalent to the weight force, right? That's an FW. So solve for the weight force. Mass times gravity. 1.4, 9.8, 13.72, and then mu is FF over Fn. Do you need the negative in there? It doesn't matter. Mu doesn't have a direction, so it's just 8.36. The normal force is also 13.72 because they're balanced, giving you a mu value of 0.61. Is that a high mu value? It's pretty high. Rubber on road is about 0.4, I think, so that's pretty high.
You can keep the mu.
Okay? If you have to, rewrite that problem out. It just takes practice, you guys. Just does. Some kids often say to me, Mr. Bennett, you make it look so easy. And I don't mean to make it look easy. I just, because I've done these over and over and over again.
Although you do use a lot of space.
Use more space, Wyatt.
No, I will not. I will use less space. Just to hurt you for pointing that out.
All right. Let's look at number 12.
You brought it on yourself.
Oh, thanks. Oh, Wyatt, I want you to condense everything down. I insist that you do it. Peter, you should put that away. Pay attention here.
All right, I will write with my tiniest letters possible.
You should, yes, you should do that. A truck is pulling with 2950 newtons on a 590 kilogram trailer, pulling it horizontally across the surface where the coefficient is 0.2. Find the friction force again. Let's draw a picture. There's the applied force. There's friction. Is it balanced? No, because it's asking for an acceleration, right? So the FA is much greater. Is it ever a bad idea to find the weight force? Never. It's almost always one of the marks. It's mass, 590. Times 9.8. 590 kilograms. It doesn't say has a mass of. You have to pick that out from the kilograms, right? 590 times 9.8. 5782. That's equal to the normal force. FF over Fn. The mu value is 0.2. FF, the normal force, 5782. Multiply those together. 1156.4 newtons is my friction force. This is kind of, number 12 is kind of the reverse of number 11, right? Problem-wise. So here we got the friction force. On number 11, no, we had to find friction, too. We were just given, we had the applied force here. Now I'm going to use my Fnet. Applied force plus friction force. Writing out the formulas. Majority of you have learned this is a good idea. Still a few people I need to convince. I will bring you to the light side. That's our net force, and with the net force you can find the acceleration. Okay, 13. How much force is required to start a 4.1 kilogram object sliding along a horizontal surface if the coefficient is 0.18? So we've got mass of 4.1, and the coefficient is 0.18, right? Again, start with the weight force. It's never a bad idea. In fact, it's probably, if you count it up, I bet you it happens at least 3 or 4 times in the test. I bet you it's worth 3 or 4 marks just doing that on the entire test. Right? If you've got a blank, you've drawn a blank completely on a problem, start with that. Get something. Normal force, same thing, same number. Mu is FF over Fn. New value 0.18. We're solving for FF. Fn 40.18. Multiply 7.23. Technically, you need a force. If that's the friction force, you need an applied force slightly greater than 7.23. I didn't get too excited about that, about whether it was greater than or not. Okay, let's look at the one on Jupiter. This caused some problems, right?
Yeah.
You need to be able to handle unique situations. And all that I've done here is I've just changed the acceleration. That's all I've done. Does it matter that it's on Jupiter or anything? No, it's not even on Jupiter. It's a moon of Jupiter. No one cares. All it is that the acceleration is different. Mass of 1.6. The d, the displacement, the distance is 6 meters. I had all sorts of people writing VI is 6 and average velocity is 6. 6 meters, you guys. It's a height. It's a distance. And the time is 2.66. What is the acceleration? Right? Let's work backwards. A equals delta V over delta T. Do I have the change in time? Yeah, it's 2.66. Do I have the change in the velocity? Some people used 6 there. No, that's the distance. I do not have change in velocity. How do I get change in velocity? Well, that would be delta V is equal to VF minus VI. Do I have the initial velocity? I guess I do. It's 0, right? Do I have the final velocity? Do I know how fast it's going when it hits the ground? I do not. Would it be easy? Would it be nice if you guys could do this? Yeah, I guess, but you can do it some other way. Start over on the right. I need to know delta V. How do I get delta V? Or how do I find VF? You probably need V bar equals VI plus VF over 2. But I don't have V bar, so I got to find it. V bar is D over T. That's step 1. Cole, you should be listening. I'm talking. You got 4 or 4? What did Dylan get?
You got 0 and 4.
Then neither one of you should be talking.
I don't want to.
Listen. Yeah, I don't know what's going on here.
Computers like normal physics.
Yep, done. V bar is D over T, so it's 6 over 2.66 is 2.26 meters per second. Got that right?
Yeah.
It's good. It's a good start.
Yeah.
With that, you can find the average velocity. Oh, that is the average velocity over here.
I tried finding acceleration.
Right? So 2.26 is equal to 0 plus VF over 2. So 2 times that, 4.51. Now we've got that. Is that equal to my delta V?
Nope.
Yeah, it is, because the VI is 0, right? And now you can plug that in up over here. Because it's asking for what is the acceleration. So it's 1.7. This is just a made-up thing. Really, is that any different than a kinematics question that we did like 2 units ago? Exactly the same, it's just vertical. Because back to our problem at hand here. What is the value of the force of gravity? It specifically says value of the force of gravity. I am asking the weight force. The value of the force of gravity. That's the weight force. What's the mass? 1.6. What's gravity on this imaginary moon? Not 9.8. You just figured it out. It's 1.7. You just figured it out. 2.7 newtons. If you haven't done about 20 problems up to this point, you're not going to get a question like that. It takes practice, which is why I provide solutions for you. I can't emphasize that enough, you guys. Well, we got lots more to go here, don't we?
Hey, what did you get on this one? 4.
Okay, the Boy Scout one. Okay, the key here is that the final velocity at the peak is 0, and I know I pointed that out to you on a few occasions. The total time is 6.5 seconds, which means that the time up is equal to the time down is 6.5 divided by 2, or, am I going too fast? 3.25 seconds.
I did that.
Okay? You have to divide the time by half. Okay? You got to split this thing into 2 parts. The going up and the going down. And keep in mind the acceleration is minus 9.8. You're trying to find the height, right? If you used 6.5 in a calculation with distance, it's going to find the total distance traveled. So you have to split it in 2. You're only interested in the height, half the trip. Okay, from the acceleration, I can get delta V over delta T. Minus 9.8 is delta V over 3.25. How much does the velocity change on the way up or the way down? The answer is minus 31.85. All right, here's the point where you use the fact that the velocity at the peak is 0. So either you've got a VI of some unknown value that you launch it at, and it goes to a VF of 0, or you could say VI is 0, and then on the way down, what's the VF, right? Well, this and this are going to be the same. It doesn't matter which one you use. V bar is VI plus VF over 2. I said the final velocity is 0, right there, which means the VF is 0 here, right? And because the delta V is minus 3.85, that means that the initial is 31.85. It went from 31.85 up to 0, which is a change of minus 31.85. The VI is 31.85. You guys got to pay closer attention. You can't have side conversations. You have to stay with me the whole time. Don't lose focus. The number one thing you can do in here is stop talking to your neighbor. Seriously. I'll do it this way for you. Final velocity at the peak is 0. Right? The initial velocity is 31.85. It's launched at 31.85. It changes by minus 31.85, which means it goes to 0. And now I find my v bar. I'm sort of doing things out of order a little bit here. Divide by 2. You get an average speed of 15.925. Solving for D. Time, make sure you use the right time, 3.25, that's the time up. And you get a displacement of 51.8 meters. I changed this one down to 2. The elevator problem. I guarantee you this question's going to be on the exam. Guaranteed. It might be multiple choice.
I'm going to read it.
There's a variety of ways that you can show this, but he's standing on a scale. Okay, Cole, enough. Try to relax. 71 kilogram man standing on an elevator. It's reaching the end of his ride to the bottom. Is he going to weigh more or less? More. What's his regular weight force? 71 times 9.8, which is? 695.8. Thank you. 695.8. But he weighs more. How much more? Well, 71 times 2 more. 837. Right? He weighs more. You add on the mass times the acceleration. Oh, there's a couple more.
What is the answer there?
This is 142. I guess I could do that, man. 837.8. Was anyone surprised by 17?
No, 17 is...
17 should not have been a surprise at all. This is Kyle flying a helicopter. It's just a guy in a balloon dropping his wall. That's the only difference. Substitute the guy's name for Kyle and balloon for helicopter. Man is in a hot air balloon that's slowly rising at a constant 4.2. He drops his wallet over the edge of the basket. After 7.4 seconds, what is the wallet's velocity? A equals delta V over delta T minus 9.8. Change in velocity of minus 72.52. Try to focus, you guys. Try, Graham. Why not? You've seen problems like this. You know how many times I've done this problem? Like I did it once on the answer key. I did it once as Kyle, and I'm doing it again, and I do that every semester. No wonder I make it look easy. Oh. If I said Kyle is now riding a helicopter, or Kyle is now riding in a hot air balloon, really?
Instead of giving 4.5, I would have
Yeah. As soon as you said a man, I was like, this is the same question.
Yeah.
It had to be Kyle.
I think it works.
The initial velocity is not 0, it's 4.2. The wallet is traveling up at 4.2. There was a few people that had set this up right and then solved it to the other side wrong. Fortunately, I'm a good guy and I followed that through and you got 5.5 out of 6.
Yeah.
You're welcome. And that only happens because you guys show your work, that I can do that. So thank you for showing your work. Add 4.2 to both sides. You get a final velocity of minus 68.32. You've got 76 point something. You need to look at that and figure out what you did wrong.
Mr. Ben, for some reason, I put minus 68.32 and you like circled.
Oh yeah, maybe I was circling it with glee. I was happy that I saw
Circle the
it.
minus.
Yeah, you
Oh.
put the minus mark. I think I lost the mark for that.
Okay, I'll have a look. Okay, so the wallet is traveling minus 68.32, but we want to know how far it has fallen. To know how far, you need to find average. The initial is 4.2. The final is minus 68.32 all over 2 minus 32.06. What's the next step? V bar. You're trying to find out how far it has fallen, right? D over T minus 32.06 time 7.4. The wallet falls 200 minus 237.2 meters. Kiss it goodbye. Goodbye, wallet. But as in the example question, how far below the balloon is the wallet? You got to remember that the balloon is traveling up. How fast is the balloon traveling up? 4.2. Time? 7.4. Same time. So the balloon goes up 31 meters. So how far below the balloon is the wallet? What's the total displacement or the total distance between the two? You're going to take 237.2 down, and you're going to add 31 because you want to know the distance between them. 268.3. And that should have been out of 6. There was one test that I only gave the person 4 out of 6 for some silly reason. So make sure you got what you deserve.
So do I get a half mark since I'm changed for that?
You can almost bet that this question will be on the exam. This question tells me if you know what you're doing. Okay? You got to break it into components. Is it ever a bad idea to start with the weight force? Never. Weight force. Mass times gravity. 22 times 9.8. 215.6. As soon as you've got a force at an angle, is it ever a bad idea to break it into components? Never. You can get 3 out of 7 just by doing this.
I did that and then I erased it. I was wrong.
F cos theta. Why didn't you have it on your examples?
I did have it on example.
And why did you think it was
I
wrong?
was like, oh no, it's wrong. And then I erased it. Alright, I scribbled it out after. Yeah.
Well, if you practice enough, yeah.
Credit. It's not your lesson.
You can give me the mark for that?
Okay, let me get finished here so Peter can go. F sine theta. Okay, you guys, try and refocus. 150 sine 27, 68.1. Okay, refocus and listen. This is the next step is the important part here. We got the preliminary stuff, right? Okay, is the normal force equal to the weight force here? No. No. We've got a normal force up, weight force down. The normal force and the vertical component equal the weight force. Bill, give me 3 more minutes. Bill. Focus, man. I know what you were doing. Don't do that. There'll be time. I do, but I gotta get this problem solved. I want to hear all about it. When there's time, I'll hear about it. I do. Okay. The normal force then is the weight force minus the vertical component. 215.6. We're going to subtract 68.1. Try, you guys. If you give me 2 minutes, I'll be done. So you get a normal force of 147.5. Okay, it's less than the weight force because you're lifting up. Easy, guys, easy. Now, mu equals FF over Fn. Okay, Dylan, what are you doing? What What do you mean, what?
Calculator.
I'll calculate you right away.
His cake is so
Who took my basket away? My cell phone basket.
Oh no.
My mom, I think my mom needed one.
Okay. What's the mu value here? 0.18. I know it's hard to maintain focus, you guys. I get it. 26.55 is my friction force. Sometimes I wonder why I bother going through tests, really. Just a couple last comments before we wrap this up, okay? Please, please, please do not just jam this in your binder and lose it. Hang on to it. The analysis sheet is valuable. As I've said all year long, you know now what's going to be on the exam. You should, right? If you do better on that problem on the exam, bring me your exam. Come and see me. I'll show you the exam. Bring me your test. Say, look, Mr. Smith, I did better. I now know this. I'll change this mark.
But you don't give us our exam.
You can come and see your exam. I've said this over and over. This is not the end. If you can show me on your exam that you can do the problem better, I'll change this mark.
Really?
Yes, that's why I give you this. If you guys would stop yapping and listen, I tell you all this
I
stuff.
give you on the exam.
You get set.
Oh, the 7.
I'll change that to a 6.
Really? But then your final, if I said really good on the exam, final would be my overall good ranking.
So?
Mr. Bennett. He's not Bennett. They say you got like 6.5 on the test. Say I got like 7 or 7 on the
I'll change it.